Okay, so this is part 2 of the 2018 Core Pure paper, and we're going to start off with question 6 now. So we want to use the standard results for the series summation to show that this particular thing is true that we've got here. So we don't know how to do something when it's squared like that, so we better start off by expanding that. So our 3r minus 2 squared is the same as the sum from r is 1 to n, of, when you expand this, you get 9r squared minus 12r plus 4, which we know is the same as 9, the sum from r to 1 of n of r squared, minus 12, the sum from r equals 1 to n of r, plus the sum of this n times is just 4n. Now, the standard summation series for r squared is a sixth n. I can never remember this one. I might need to check it. A sixth n, n plus 1, 2n plus 1? No, let me just double check. A sixth n, n plus 1, 2n plus 1. I would need to use the formula book for that. A sixth n, n plus 1, 2n plus 1, minus 12 multiplied by a half n, n plus 1, plus 4n. Okay, let's do a little bit of simplifying. 9 over 6 is 3 over 2. So we have 3 over 2n, n plus 1, 2n plus 1. 12 over 2 is 6, that's minus 6n, n plus 1, plus 4n. They've factorised by a half n here, so I'm just going to take a half n out of everything. If I take a half n out of this, I would be left with 3, n plus 1, 2n plus 1. If I divide this by a half n, I'm actually going to get minus 12 n plus 1. So you're dividing by a half, in other words, you're doubling this. And this last bit is just going to be a plus 8. Okay, you can expand it to check if that works. I'm hoping this whole thing here is going to collapse into this thing. So I have a half n, 3n, whoops, let's expand brackets properly. So this expands to 2n squared plus 2n plus n, so that's plus 3n plus 1, minus 12n minus 12 plus 8. So that's a half n, 6n squared plus 9n plus 3, minus 12n minus 12 plus 8, which is a half n, 6n squared minus 3n, and that's minus 1. Great. That's exactly what we've got. Hence, find any values of n for which this horrible statement is true. I kind of love this question though. Okay, so there's a few things I want you to notice when you look at this. 1, r equals 5 here. Don't let that trick you. 2, this crazy thing here. Now, if you got stuck, you could type it into your calculator. And it will give you the answer. Because your calculator can handle this type of stuff. Okay, just have a look around. Maybe instead of typing r, you can type in x or theta or t, but I would probably just try and type x instead, and your calculator will actually do it. But I want to show you what's going on here. So I'm going to write the question out just so I don't have to keep going up and down again and again. So let's have a quick write that out. So it's from r equals 5 to n of 3r minus 2 squared plus 103, the sum from r equals 1 to 28 of r cos r pi over 2 equals 3n cubed. Okay, so we need to solve this equation. First of all, I'm going to investigate this thing. That's what I want to do. I want to investigate just this bit that I've got here. Now, we know that if r is equal to 1, let's see what happens when we substitute r equals 1 into this. It will just be 1 multiplied by the cos of pi over 2. Now, the cos of pi over 2, make sure you're in radians mode. You should know this one. I'm just going to show you my calculator. It is 0. So when r is equal to 1, we get 0. When r is equal to 2, we would get 2 multiplied by the cos of pi. Now, the cos of pi, if you think about what cos of pi is minus 1, so it's just minus 2. When r equals 3, you would get 3 times cos of 3 pi over 2. And you can guess what 3 pi over 2 is going to be when you take the cosine. It's 0. So you get 0. Then when you get r equals 4, you'll have 4 times cos of 2 pi, which is just going to be 4. So you can predict what this next one's going to be. Whoa, okay, when r equals 5, we know it's just going to be 0. So it looks like we've got a pattern here, and the pattern is 0 plus minus 2 plus 0 plus 4 plus 0. Why I put brackets around the 4, I don't know. Plus, the next one would be minus 6. It's just going to change this whole sequence like this, and it's going to keep going, only having them go up and down like that, until we get to the last one, which will be 28. And you can see that the multiples of 4 are the positive ones. So, in this first chunk of 4 numbers, you have a 4 and a minus 2, so it all adds to a 2, because just 4 minus 2. Now this next chunk of numbers, it goes 0, minus 6, 0, 8. So you've got 8 and minus 6, which all comes to a 2. And each set of 4 numbers is going to come to a 2. There are 28 numbers, and each set of 4 is 2. So the sum from r equals 1 to 28 of r cos r pi over 2, there are 7 pairs which each add up to 2. Not pairs, sorry. There are 7 groups of 4 which each add up to 2, which is 14. Now all of this work here is probably worth 1 mark, and you could just type this in your calculator. So the bit I've underlined in red is 14. Let's actually do some of the normal bit of the question. Like I said, try and type this in your calculator, just this red bit, and you will come up with 14, and you can do that. So this first bit between 5 and n, well, we normally do it between 1 and n of 3r minus 2 squared. And if we do it between 1 and n, we have to subtract between 1 and 4. Remember, you don't subtract all the way up to 5, you subtract to the 1 below it. And we've just worked out that this thing here is 14. So that's plus 103 times 14 equals 3n cubed. Okay, this we have also worked out earlier on. It was a half n, 6n squared minus 3n minus 1. This one, we can just substitute in n equals 4. So it's going to be a half times 4 times by 6 times 4 squared minus 3 times 4 minus 1. Or you could type it in your calculator. Plus 103 times 14, which is 1442, equals 3n cubed. You've got to just keep sticking with this, because this is pretty unpleasant. I'm not going to do anything with this just yet. I'm just going to leave it as a half n, 6n squared minus 3n minus 1, and I'm just going to work out what this whole long stretch is. So a half of 4 is 2, so that's 2 multiplied by 6 times 16 minus 12 minus 1, which is 166. So that's minus 166 plus 1442, which is 1276, equals 3n cubed. Oh my god, this question is kind of long. Okay, so we're going to multiply everything out and see what happens. A half n times 6n squared, that's 3n cubed. You then get minus 3 over 2n squared minus a half n plus 1276 equals 3n cubed. Luckily, the 3n cubes are going to cancel on both sides, so we just end up with minus 3 over 2n squared minus a half n plus 1276 equals 0. Get your calculator. Who's going to bother when you're in the panic of an exam? So we'll do the polynomial, so that's minus 3 over 2. The polynomial solver, and we're going to put in minus 3 over 2, minus 0.5, and 1276. And we get that either n is equal to 29, or n is equal to minus 88 over 3. But n is a positive integer, because that only works for series if it's a positive integer. N is a positive integer, so n equals 29. Pretty crazy, but you could just type this in. I'm actually going to show you that. So if I just really quickly go to math, sum of the series, so what does it say? X cos x pi over 2. I'm in degrees mode, so it might not work. I'll have to change that. Okay. So you can actually type it in like this. I'm just going to check that I can see it on here, that it's in the right place. Let's hold that right there. So you can see it like that. And when you press equals, it does just give you 14. I'm not sure if you can see this. Sorry if you can't. Okay, mark scheme. That bit we knew we got right because it came down to here, and n is 29. I'll leave it here if you want to read through how it's done, but you only get one method mark for doing this expansion bit. I wonder if you have to do that. Let's see. This may be implied by a sum of 14. I mean, literally, you could just type it in the calculator. You don't even have to do it. You could just type it in your calculator. So all this bit in red and purple, if you want, put it on that graphics. Okay, question 7. This is hard, this one. If you were in my class, you may have recognized this from before. I hope you remembered it. So we've got this equation, and it looks like it's a roots of polynomial question. The equation f of z equals 0 has roots z1, z2, and z3. When plotted on an Argand diagram, the points representing z1, z2, and z3 form the vertices of a triangle of area 35. Given that z1 equals 3, find the values of p and q. Okay, what I like to do to begin with is I like to remind myself that this one is minus b over a for the coefficients, and it's the sum of the roots. This one is c over a, and it's the sum of the root pairs. And this one is minus d over a, and it's all 3 roots multiplied by together. Okay, I find that useful as something visual. And in this case, clearly a is equal to 1 for this z cubed that we have. Okay, now if we know that z1 is equal to 3, we know something quite special about z3. Now remember, these are just the same as alpha, beta, and gamma, okay? If this one is real, and it's a cubic, then you must know something about these two. They are complex conjugate pair, which is very special because you know that they have the same real part and the same imaginary part, but one is positive and one is negative. That is going to be really, really important. The next thing that I think is useful is that we know the sum of the roots is minus b over a, and b is 1 and a is 1. So this tells me that the sum of the roots is minus b over a. It's just minus 1. Well, let's have a look at this and see what happens. So I know that the sum of the roots is minus 1. So that means 3 plus a plus ib plus a minus ib is equal to minus 1. Well, they cancel. So you get 3 plus 2a is equal to minus 1. 2a is equal to minus 4. So a is equal to minus 2. Right, so now we know something about them. We can actually do a bit of a sketch to see how this might help us. Okay, so one of them is at the point 3. The other ones are at minus 2 plus something and minus the same amount of thing. That distance coming up there is b, and the same distance down here. So we've got a triangle, right? Now if I draw on this triangle and we want to find the area of this triangle, well, we don't want to find the area. We know that the area of this triangle is 35. All you need to do is really tilt your head. This is the base of the triangle, and this is the height of the triangle. Well, if that's b, that's also b. So the base of this triangle is 2b. The height of this triangle, well, that's 3, and that's 2. The height is 5. So we know that the area of the triangle, which is a half times the base times the height, the area of the triangle is 35. So when I solve this equation, I get 5b equals 35, so b is equal to 7. This now tells me that z1 is 3, z2, which is a plus ib, is minus 2 plus 7i, and z3 is minus 2 minus 7i. And they want us to find out what p and q are. Well, p is c in this case, so the sum of the pairs is going to be p over 1. So the sum of the pairs is going to be just p over 1. In other words, p is going to be equal to 3 multiplied by this plus 3 multiplied by this plus this multiplied by this. Now, if you want to, you could store these on your calculator as like A, B, and C, and then you could just do A times B, A times C, and B times C. So that's probably what I'm going to do. I'm just going to say that 3 I'm going to send to A. I'm going to do minus 2 plus 7I. And I'm going to send that to my letter B. And I'm going to do minus 2 minus 7i. I am going to send that to letter C. It might save me time, it might not. So now all I need to do is A, B plus A, C plus B, C. So you should get something that's kind of looking a bit like this. I'm just going to check on my camera so I can actually see what's going on. You get something that looks a bit like this in your camera. And when you put all that together, you can just go straight in with the answer so that P is equal to 41. We then know that Q is the D sort of bit here, so it will be minus Q over 1 is them all multiplied together. So minus Q over 1 is the 3 roots being multiplied. The three roots being multiplied, well, I've already got them stored, so I can just do A times B times C in my calculator. And we get 159. So 159 is equal to minus Q, so Q is equal to minus 159, and P is 41. Really, really hard question, but when you look at the page, there's not actually that much maths. There's a lot of thinking that's going on in this one. Okay, let's just double check we've got that right. There's many, many different roots for this, so yeah, we just, as long as we've got the right answer, that we got minus 159 and 41. And I think, did we do it in the same way? Yeah, we've got something to do with the sum of the roots, finding out what alpha is. They used alpha and beta rather than A and B. So it can be quite confusing when you read a mark scheme, and it's different to your one. Okay, we're going to keep pushing on. We're going to do some proof by induction questions, and then we're going to do, I think it's a volume of revolution. So, proof by induction. We want to prove that this thing is true. So first of all, we need to show that it's true for n equals 1. So left-hand side, we get 5 minus 8, 2 minus 3 to the power of 1 is just 5 minus 8, 2 minus 3. The right-hand side, we have 4 times 1 plus 1 minus 8 times 1, 2 times 1, 1 minus 4 times 1, which is equal to 5 minus 8, 2 minus 3. Left-hand side equals right-hand side, so true for n equals 1. Next step, assume that it's true for n equals k. In other words, 5 minus 8, 2 minus 3 to the power of k is equal to 4k plus 1 minus 8k, 2k, 1 minus 4k. Now we need to show that it is true for n equals k plus 1. So we want to say that this to the power of k plus 1, we're going to hopefully aim for it to be something. So that's going to be 5 minus 8, 2 minus 3 to the power of k, multiplied by 5 minus 8, 2 minus 3. So that's to the power of k. We're multiplying it one more time, so it's the same as k plus 1. Now, we know what this thing is. We've just assumed it. And we've assumed that it was 4k plus 1 minus 8k, 2k, and 1 minus 4k. You could write these either way around, by the way. You'll end up with the same thing. 5 minus 8, 2 minus 3. Now, this is the bit where I like to say, what am I aiming for? And I usually would do it in like a different colour, or I could cross it out at the end. So the aim that I want at the end is 4k plus 1 minus 8k plus 1, 2k plus 1, and 1 minus 4k plus 1, which I'm going to write out with it in expanded form. So that's 4k plus 4 plus 1, so it's 4k plus 5, minus 8k minus 8, whoa, 2k plus 2, and 1 minus 4, so that's minus 3 minus 4k. If I can get to this, I can then just write that line out afterwards. Okay, let's do the expansion. So I'm going to do this multiplied by this. I'm going to try and do it a little bit quicker. So that's going to be 20k plus 5 minus 16k. Then I'm going to do this multiplied by this. So that's going to be minus 32k minus 8 plus 24k. Then I'm going to do this multiplied by this. So that's 10k. That one times that, and then this times this. So it's going to be plus 2 minus 8k. And then I'm going to do this times this. That's minus 16k minus 3 plus 12k. Take it nice and big. Use as much space as you need. Which then simplifies to 4k plus 5. Excellent, that's what we wanted. This simplifies to minus 8k minus 8. This simplifies to 2k plus 2. This simplifies to minus 4k minus 3, but minus 3 minus 4k. Which we can then copy out as that one that we've got at the top. So that's 4k plus 1 minus 8k plus 1, 2k plus 1, and 1 minus 4k plus 1. So, true for n equals k plus 1. Here comes the conclusion statement. As true for n equals 1 and n equals k plus 1 when assumed true. For n equals k. Statement true. What did it want it to say for? For n member of positive integers. For n is a member of the integers which are positive. This comes from a German word, I think, which means numbers. It's a lot of work. And the next one is an induction proof to show that something is divisible by 21. So I want to take this function, what's that, 4 to the n plus 1 and 5 to the 2n minus 1. 4 to the n plus 1 plus 5 to the 2n minus 1. I better check I've written that out right, it's so easy to make a mistake. So I want to prove that it is divisible by 21. This is part 2 of the question. So first of all, we're going to say show true for n equals 1. So f of 1 is going to be equal to 4 squared plus 5 to the power of 1, which is 16 plus 5, which is 21, which is clearly divisible by 21. Now we will assume true for n equals k. In other words, f of k equals 4 to the power of k plus 1 plus 5 to the power of 2k minus 1 is divisible by 21. And now we're going to show that it's true for n equals k plus 1. Now, if you remember the trick, we're going to say f of k plus 1 minus f of k. That's the trick that helps us to do this kind of one. So f of k plus 1 is 4 to the power of k plus 1, which is 4 to the power of k plus 2, plus 5 to the power of 2k plus 1 minus 1. So that would be 2k plus 2 minus 1, which is 2k plus 1. And that's all going to minus 4 to the power of k plus 1. We're now minusing this, minus 5 to the power of 2k minus 1. So what I think we want to do is we want to make this thing look like an f of k. So I can pull down a 1 from here. So it is going to be 4 to the power of 1 multiplied by 4 to the power of k plus 1. And this one I need to pull down 2 things from it. So I'm going to pull down a 5 squared multiplied by 5 to the power of 2k minus 1. Notice I'm trying to make these powers match these powers here. Okay, the aim is to make the powers match the ones that I have in f of k. I'm trying to match everything to this. So I pulled down a 2 so I could reduce that to a minus 1. And then I've got minus 4 to the k plus 1 minus 5 to the 2k minus 1. So I've got now 4 minus 1, 4 lots of the 4k plus 1 minus 1 lot of that, which is 3 times 4 to the k plus 1. And then I've got 25 lots of 5 to the 2k minus 1 minus 1 lot of 5k to the 2 minus 5 to the power of 2k minus 1. So that's 25 minus 1, which is 24 multiplied by 5 to the power of 2k minus 1. This is the tricky bit. If I break this 24 down, I can break it down into, because I'm trying to find out how does 21 relate to these. It breaks down into 3 lots of 5 to the power of 2k minus 1 plus 21 lots of 5 to the power of 2k minus 1. I want it to be to do with 21 because that's when it's divisible. Let's bring this back down here because I think I'm going to need it. So we have that f of k plus 1 minus f of k is equal to, well, this thing here is f of k, but it's just been multiplied by 3. Plus 21 times 5 to the 2k minus 1. All we need to do now is add the f of k back on. So it's 4 lots of f of k plus 21 multiplied by 5 to the power of 2k minus 1. Clearly, f of k plus 1 is divisible by 21 as both 4 f of k and 21 times 5 to the power of 2k minus 1 are divisible by 21. Because we know that's divisible by 21 and that's divisible by 21 because of this factor that we've got here. So all we need to do is a concluding statement. Hence, because true for n equals 1 and n equals k plus 1, when assumed true for n equals k, it is true for all n as members of the positive integers. Okay, we don't really need to check the mark scheme here, but it's 6 marks. I'll just tell you where they come from. So you get 1 mark for showing that it's true for n equals 1, 1 for showing that you've assumed it to be true for n equals k, a method mark for doing some manipulation, and an accuracy mark for getting it presented in the right kind of direction, and an accuracy mark for being presented in the correct way, and an accuracy mark for the final statement. You then also get this same idea here. You get 1 for showing that it's true with n equals 1, you get 1 for the assuming true, and then you get some method marks and some accuracy marks, and then that final statement. The bits that are underlined are the bits that need to be mentioned. Okay, we're nearly there. My hand is getting pretty tired, but we're going to just do this last question. Hopefully it's not too hard, but I know it kind of is. Okay, so we've got a bottle here on the left and then a diagram on the right. A mathematics student is modelling the profile of a glass bottle of water. Figure 1 shows the sketch of a central vertical cross-section, and you've got all the letters going around the outside of the bottle, with the measurements taken by the student. The horizontal cross-section between CF and DE is a circle of diameter 8 centimetres, and the horizontal cross-section between BG and AH is a circle of diameter 2 centimetres. So all they're really saying is that this is a circle here, and this bit at the top is a circle as well when it's a bottle. So it's basically consisting of these kind of different sections. There's a cylinder, a funny shape, and then a cylinder. The student thinks that the curve GF could be modelled as a curve with this equation here. These bits are clearly going to be easy. This top cylinder and bottom cylinder is just GCSE maths. This is the hard bit to find the volume of. A student thinks that this could be the equation where A and B are constant and O is a fixed origin as shown in figure 2. Find the value of A and the value of B according to the model. So it looks like they've tried to change it into coordinates. So let's just think. F's coordinate, it's got an X coordinate of 4 and a Y coordinate, well, it's gone up 14, so I'm going to say it's 4, 14. G has an X coordinate of 1 and G is all the way up 14 plus 4, that is 18. And we know that the equation is going to be ax squared plus b. And we've got two coordinates, so we can do some simultaneous equations. So we have one of the coordinates, is 118, and the other one is 414. We think that it is going to be y equals ax squared plus b, so I'm going to take these coordinates and substitute them in. So that is 18 equals a plus b, and 14 equals x is 4, so it will be 16a plus b. Now I'm feeling really lazy by this point, so I would probably go to my simultaneous equation solver. And I've got two unknowns, so I'm going to do that. I've got 16a plus 1b equals 14, 1a plus 1b equals 18. And you get some surprising, horrible numbers. You get that a is minus 4 over 15, and b, just to make you think you've done it wrong, but you haven't, is 274 over 15. Only 2 marks. Use the model to find the volume of water that the bottle can contain. Okay, so we have got cylinder number, well, let's see, we've got this shape to begin with, number 1. We've then got a small cylinder and we've got a big cylinder. And it looks like the whole thing is going to be rotated about the y-axis. If something is going to be rotated about the y-axis, we know that the volume is going to be equal to pi, the integral of x squared dy. Well, good job we've worked out that y equals minus 4 over 15 x squared plus 274 over 15. So I'm going to need to make x squared the subject. So I'm going to multiply everything by 15 and then divide by 4. So that's 15 over 4y equals minus x squared. And then I'm going to do that multiplied by 15, but I can just get rid of the 15 and divide by 4, which is 137 over 2. So when I rearrange this, x squared is equal to 137 over 2 minus 15 over 4y. So the volume is pi multiplied by the integral of 137 over 2 minus 15 over 4y with respect to y. We just need to put in the limits for y. Well, for this section, the y limits are between 14 and 18. So I'm going to do 14 and 18 here. I'm going to leave pi outside the front and I'm going to integrate. So I get 137 over 2y minus 15 over, well, I'm increasing the power to 2 and I'm going to also divide by that. So it's minus 15 over 8y squared, and that's between 14 and 18. So I'm going to substitute 18 into this. I'll store it in my calculator. So that's 137 times 18 over 2 minus 15 times 18 squared over 8. So you get 1251 over 2. Now I'm going to do the same thing with 14, which I'm going to subtract. So it's 137 times 14 over 2 minus 15 times 14 squared over 8, which is 1183 over 2. So I'm going to do 1251 over 2 minus the answer, and we get this all comes down to 34 pi. So this is shape number 1. Shape number 2 is my tiny little one at the top, which has got a radius, a diameter of 2, so a radius of 1 and a height of 10. So for this one, it has a height of 10 and a small radius of 1. So the volume of this is going to be pi r squared h, which is just going to be pi times 1 times 10, which is just 10 pi. My third cylinder is the big cylinder, which has got a height of, I think, 14. Yep, and a radius of 4. Diameter is 8, so radius is 4. Now volume is pi r squared h, that's pi times 4 squared times 14, which is 224 pi. We are nearly there. So the total volume is equal to 34 pi plus 10 pi plus 224 pi, which is 268 pi, which is 842 centimeters cubed to 3 significant figures. Wow. Okay, we've literally got 2 marks left. State a limitation of the model. Well, the glass here is being modelled as just like a infinitely thin line. So really what we need to say something here is we could, the model doesn't take into account the thickness of the glass. I'm going to show you in the mark scheme the other things you could say as well, because there's many. And then part D of the question says, the label on the bottle states that the bottle holds approximately 750 centimeters cubed of water. Use this information and your answer to part B to evaluate the model, explaining your reasoning. Now, even if you got part B wrong, you can still get this mark for making a comparison. So we think there's going to be 842. So we can say 842 is much larger than 750. So this is not a very good model. It may be that the numbers are really close, in which case you could say that it is a good model. But here, it's really far away, it's not a very good model. Okay, we are done. Let's just look at the mark scheme. Okay, so there's the ugly values for A and B, and then the volume came out as 268 pi. You get a mark for just in the cylinders, a mark for setting up the integration, and you get a method mark for it being with the 18 and the 14. They just pulled out the 4 to the front, so they didn't have the 4 with both of these, but I don't think that really affected us. And you did come up with the total bit being 268 pi. This was the thing I wanted to show you. There's so many things you could say. The measurements may not be accurate, the curve may not be a suitable model, the bottom may not be flat, the thickness of the glass may not have been considered, the glass may not be smooth, blah, 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 blah. There's loads and loads of things, okay? Has to be stuff to do with either the dimensions, the model of the curve, or how simple the model is. And then again, you can just see about that comparison. If you've made it to the end of this, well done. It's a pretty tough paper. That was the first Further Maths AS paper that there was, and I think people probably would have found that quite tricky. Okay, hope it went well for you. Bye.